Hello all, in this video we are going to demonstrate our project Hardware Accelerated Network Intrusion Detection System. I am Divya and my teammates are Darshan, Shubham and Surya. Before starting, let's look into a quick animation.
This is Jay. Jay is a TSA officer. Jay's responsibility is to protect the security of the country by making sure no illegal items like guns or ammunition are entering the border by checking the bags. Jay's work at times can get really tiring. He has to check a bunch of bags quickly and thoroughly. Sometimes an exhausted Jay becomes slow and misses a couple of things while checking. This leads to a frustrated passengers and a security threat. To resolve the situation, Jay installs a bag scanner capable of detecting illegal items based on the set rules. This thus helping Jay focus only on the bags that are marked as a potential threat by the scanner. This improves the speed and also enhances the security. A similar situation can be seen with respect to network security, where J, our TSA officer, maps to existing network firewalls, and the bags are similar to data which can also contain malicious information. What we need is a robust security like the combination of J and the scanner, which would be a network intrusion detection system.
But before looking into a network intrusion detection, let's look into why we need network security. Smartphones and smart living have become an integral part of our lives. This means almost everything, be it home security, phones, watches, and maybe even refrigerators, are a part of network and connected to the internet. And they might host some amount of data on it. But are these networks secure and reliable? Well, the answer is not completely. And this is because of a rapid growth in terms of cyber attacks and cybercrime. 2022 saw a significant growth of 38% in terms of cyber crimes and cyber attacks. And what are its effects? Well, loss in terms of billions and trillions of dollars. The question is, how do we protect our data? What's the current state of our network security? Let's look into our network security with this example. You, as a client, request your bank for information. The bank, the server, responds, but you have an intruder waiting to access this data or corrupt it. What we need now is a mechanism to block such intrusions. Our current networking solutions provide for a simple firewall system which can provide basic security, but it isn't reliable. It is susceptible to clever attacks and can be bypassed. This calls for a strong and robust system for security, which is our network intrusion detection system. And one such network intrusion detection system is SNOT.
It is understood that we need some sort of an intrusion detection system to protect our network, and one of such system is the SNOT application. SNOT is a network intrusion detection system. It is used for analyzing the packets sent in the network, and it is open source and it's a rule-based detection engine. SNOT has basically three modes of operation. One is sniffing. It listens to the packet that is streamed, and the second is logger. It logs the any alert or any intrusion that is detected. And network next is the network intrusion detection, which is deep packet analyzing uh, analyzing tool. It is a rule-based tool. So, how rules are defined is like, say, suppose we defined a rule to alert for the word missile or say bomb. So when it finds that when it marks that word in the packet, it sends to the SNOT application where it sends an alert or drop the packet depending on the rule that we set, and then it drops the packet. And suppose we have a mm, some word like hello or something in the packet, it doesn't have to report anything in the SNOT application, so it just passes the packet to the destination. So this is how the SNOT runs. With the increase in attack day by day, the cybersecurity has been a big concern. Companies have started investing in network security like cloud security and machine learning to protect from these kinds of attacks. So here is the trend of the budget spent by the companies for cloud security, um the employee awareness and training over the period of 5 years, how the trend is increasing and will increase in cybersecurity budget. Snort has been used by various industries where the data protection is of utmost importance, like sectors like IT, computer, where data is flowing every day, millions of data is flowing every day. So where data protection is of utmost importance, but Snort alone is not sufficient. Software alone will not be able to process all the traffic at full link rate. 80% of the CPU time is consumed in string matching task alone, and software is relatively slow compared to hardware. This is where our network intrusion detection system gives us best. It's called HANDS, Hardware Accelerated Network Intrusion Detection System. Just like how we trust our parents who is very protective of us, Hans is there to protect you from any kinds of attacks, and it is a very trusted system. This is the overview of how our Hans system works. Say I'm the sender who wants to communicate to my teammates Shubham, Darshan, and Divya via WhatsApp. Their nodes are N1, N2, and N3. And I'm trying to send a message to them via WhatsApp, and I basically maintain a rule uh, which which knows their destination, and the message which I'm sending is received by the hands network and system, and it tries to matches with the destination uh, of my teammates, and if it finds a match which is maintained in the rule, then it it is a valid address, and it passes the message without any issue. Say suppose we have an intruder, node N4 in this case, and who wants to listen to what the message is, who tries to listen to the data which I'm sending, and then in this case, the hands will again cross-validate the addresses with our rule. If it doesn't find any match with the address which is maintained in our memory, then it will drop the packet. So this is how our hands system will protect from any kind of attack.
Now let's look into the working of hands. The main components are hardware accelerator and dual core processor. Here the hardware accelerator works like the backscanner from the analogy and lets the processor know that the packet might contain malicious content using a signal. If a match is raised, the processor is activated to perform deep packet analysis. This helps us speed up our network intrusion detection process by avoiding inspection of every incoming packet and analyzing only the suspected network packets. As we can see, the incoming network packet is simultaneously being sent to the hardware accelerator and to one of the cores through the arbiter in round-robin fashion. Here the accelerator does not raise a match signal, so the core is not activated and the packet is passed on to the output queues. For the second packet, the match signal is raised, which activates the core to perform deep packet analysis, and the core determines that the packet has malicious content. As a result, packet is dropped. Similarly, the match signal is raised again for the third packet, but after performing deep packet analysis, it determines the packet does not have any malicious content and is passed on to the output queues through merge module. Hardware accelerator is designed using Bloom filter. The Bloom filter has three hash functions and an array. The array's value is preloaded based on the predetermined malicious pattern, which are passed on to the hash functions and bits are set. And the hash functions can generate same indices for different patterns, which might cause a false match or a false positive. This calls for deep inspection using the processor. The green packet is a no match, so we can see that all the bits indexed by the hash functions are not set, indicating a no match. For the second packet, all the bits indexed by the hash functions are set, which indicates a match. For the next packet, the bits indexed by the hash functions are set, indicating a match. But as we discussed earlier, the second packet shows a false match and the last packet is a true match. As the malicious pattern can be distributed across multiple network packets, we concatenate incoming network packet with the previous network packet and look for the malicious pattern across 8 consecutive 7 bytes. If a match signal is set from any one of the 8 combinations possible, we send the match signal to the processor. Now let's look into the architecture of our dual core processor, which is a 4-way interleaved multi-threaded RISC-V based processor. Thread 1 work on the source address to find if there is any intruder, sending some malicious packet to the receiver. Thread 2 works on destination address so that the data isn't sent to any unauthorized receiver. Thread 3 and thread 4 looks for malicious pattern in the payload. These thread 3 and thread 4 uses rule memory, which is specifically used to store known malicious pattern and used to compare with the payload. If there is any malicious pattern is present, then the packet will be dropped.
Now I will start showing the demo for our final design. So here we are doing 2 layer of protection. We'll do IP header as well as pattern. So basically what we are doing is we will check for source and destination IP, and if there is a malicious source or destination IP, we'll basically drop that packet. And also we have put one missile as our packet which we want to drop, and we'll drop that packet. I'll just go to the control node and set up all the IPs, and I'll download the bit file and then basically do the RKD for the routing table. So yeah, like I was saying, so we are doing we have multiple threads and multi-core system, like already mentioned in the slides before. So our threads are working on different parts. There will be 2 threads which we working on the checking the source address and the IP destination IP addresses, as well as the other 2 threads will be working on checking the pattern and basically comparing if it's a pattern that we need to drop or not. Alright, so this is how basically we will have multi-layer protection, not in terms of only like bad information, but in terms of like someone is we are getting any information from someone like we don't want. So yeah, so if you see this is what are the 2 software registers for pattern matching we have to set. So basically we have given software registers to set the key for the hash function. So basically, like mentioned in the before slides, we have a hardware accelerator to basically give us the signal, match signal, based on which we will do the matching. So if you see this 0404 0313 and this 8 will be basically our hash table we have set. So basically we are setting ones to some particular bit locations based on our pattern. So if whenever hardware accelerator will give some it will give the hardware accelerator will get some indexes, and if those indexes are set as 1, as shown in the video, we'll get a match signal. And this was the pattern for all the IP address and the missile pattern and all which we are checking. So we have set that so that the hardware accelerator will work properly. Now first we'll basically try to see, so we'll see the source. So basically like I'm saying, N3 is our malicious node or the intruder node. So from N3 we should not get any packet, or even to N3 also we should not be able to send the packet. So first we will try the source, the thread. So basically the thread which is working on the source address. So we will set N0 node as basically a server, and we will try to ping to send some packet. We'll send some file to the N0 node,
and we should be able to receive from N1, N2, but from N3 node we should not be able to receive that. Okay, so I'll set up the server over here, and yeah, so I'll use the hyperf command and the port 2000. I'll set up the server, and then yeah, so I'll go to the N1 node first, and yeah, then yeah, you can see in.txt is what I will send. It's just hello, and I have another file which is called missile.txt, which I'll use later, and it has the pattern missile which we want to drop. So yeah, these two are the files which will be using to send the packets, the TCP packet. And yeah, so using the sudo tcpdump command, I'll be hearing whatever I'm sending, so that I can see in the file that I'm able to receive the packet, and we can confirm that this is working properly. I'll just run this command on the N0 server node as well, so that server node is able to hear. And yeah, I'm just wait a second. So yeah, I'll just write over this. Yeah, so now hearing, and now from N1 node, now basically I just want to send a packet using hyperf. I'll send a packet. Yeah, so in .txt you have to change the port to 2000, just like the server. Yeah, so now the packet is sending, and yeah, this should come up. Yeah, I'll send again 1 or 2 more times, and yeah, you can see that we are able to receive on their server side. You can see the bandwidth and all which is coming. You can see the speed that we are able to receive, and also in outztxt. Yeah, see, so I was able to hear and see. This is cat. Okay, sorry, I have to open in Vim. I open in Vim, and then yeah, see, I search hello, and then yeah, see, hello is received. So basically we received the packet. I was able to send from N1 the hello packet, and in N0 I was able to hear using TCP-dump. So this is showing like from N1 to N0 communication is proper, and I am able to receive the hello packet. The hello packet will say is the good packet, and the missile is the bad, the intrude, the packet that we want. Because like network, like just like airport security and all, we want to intrude, basically stop some attack on missile or grenade, anything that you want. So we have taken that reference and used that missile thing over here, just like for security. So yeah, so we'll move ahead with the demo, and now from N2 node I'll just send another packet just to show like N1 to N0 communication I've sent. Yeah, you can see here N2 to N0 is also I'm able to send, and yeah, in the file also I should be able to receive. So I'll just open the file also again, outztxt, and here hello still. Yeah, see, now also hello is there. So basically from N1 to N0 I'm able to send, from N2 to N0 I'm able to send. But yeah, now when I try to send from N3, based on our pattern that we have given to our hardware accelerator, it will see the source IP, and then it will give a match signal, and now it will go to the CP mode, and one of our thread is working and checking the, so whenever the packet is coming, we know that the source IP is like after 4th offset from the header pointer, and we are taking that whole location and we are manipulating, and we are comparing with the reference rule that we have given. And you can see the outztxt is basically empty, right? So yeah, so if you can see, this was empty, and now again I'll go from N1 node, and N1 node, see, again I was able to send. So from N1 node I was able to send, but outztxt I was not able to send. Okay, so sorry, yeah, N3 node I was not able to send because N3 node is dropped. outztxt showed the thing that, like I was saying, outztxt was empty for N3 node because the packet was dropped, but N1 it was there. Yeah, now we'll go, and basically this was this confirmed, like from N3 node we are able to not get the packet. Now I'll just try the destination part that I was saying, that see, N0 node we were able to send packets, and N0 node as a server was working fine, but N3 node now as a server should drop all the packets that it is getting, because N3 is, like I said, that same IP we have given as the reference rule for both source and destination. So that IP address we have given in the reference rule file. In references rule we are using just like we are using a memory, and from that memory we are taking all the rules that we have stored. So we can extend the rules also if we want, but yeah, so N3 node is already there, and for both of the cases, either source and destination, that address will be taken and it will be compared. Yeah, so N3 node I've set up the server. Now basically I'll run and I'll go to N1 node, and from N1 node I'll try to send something to the N3 node, and I'll send the same int.txt, the hello word, the hello packet only, which is the fine packet which we were able to send since now. And yeah, so N3 node I went, and now I'll just here TCP dump using TCP dump over here, and yeah, from N1 node I should send it, and I'm sending. So yeah, see, I'm not able to send, and I'll just do once more. So yeah, see, we are not able to send it, and then I'll go to N2 node to say that not only from N1, from N2 also. So it doesn't matter from which node like you want to send, because our destination is not, so let's say like it's a friend network, or like people who are talking amongst themselves, and there is an intruder like N3. So we don't want to send outside our secure network. So N3 is sitting outside our secure network. So it doesn't matter which node you are, from any node you are not able to send to N3. So like I showed, so this shows like the destination part of our working. So like I said, other than the pattern, we have like IP header section also implemented. Like two threads are working on the source and destination IP also. So that pattern, that matching also of our address is happening. So based on that, we have two layer of protection, not only in terms of packet, but in terms of this also, that we are not sending to some other random IP address, some outside of the network communication. So now like I showed this, I'll just show. So destination, when the server was at N3, we were not able to receive the packet, right? So now I'll create the server over N2 node, and I'll just send the packet again, okay, from N1 node, to show that okay, I'm still able to send the packet. So I'll go to N1 node, I'll go N2 node over here, and then I have to create a server. I'll create a server at N2 node, and yeah, so yeah, using iperf, I'll create a server. Yeah, port 1234, and then basically I will just have to run, I'll run TCP dump over here and to node also, to just hear the packet. Yeah, I've config, but no port is there, ETH4. Okay, I'll hear on ETH4. So TCP dump ETH4, and yeah, I'll just write in the out ctxt, and yeah, now server is there, and we are hearing through TCP dump. That is also done. Now from N1 node I have to just send the packet. I'll send the packet. Yeah, into node, and port is 1234, and in.txt is my file. I'll just send, yeah, so ampersand, this should come. Yeah, so I was able to send. So see, because this was proper N2, like N0, N2 is like a proper server node and like a trusted communication. So I'm sending from N1 to N2. So yeah, previously in between we showed from N3 we were able to not send the packet to N0, but from rest we were sending. And here also we showed, like I went to N3, I showed to N3 we are not able to send from anyone, and when I go back to N2, now I'm able to send from N1. So this trusted communication and in the intruder concept that we have talked about, that N0, N1, N2 are like trusted people, and N3 is not, the it's like an intruder. This thing is working. Now I'll just show the pattern part also. So other than the IP address, in between N0, N1 also, if you send particular pattern like missile, for our case the example that we are using is missile, then that packet should be dropped. Like you should not be able to receive missile, any word. So if a message is coming which has missile or any other similar example, you can take any harmful, our system can basically detect that word and it can drop that message. So if you want to configure and basically detect some harmful things, or you want to keep track of this, you can give those words as in the rule file, and basically it will drop all of them. So yeah, so first I'll go from n0 node, and yeah, n0 node I'll create a server. So commands, and yeah, iperf I'll use to create the server. I'll create server. I'll put port as 3456. I'll start a server. Then I'll here using sudo tcp dump, and I should be able to here over this. I'll write to rgtxt. Now from n1 node I'll send a packet. First I'll try to send a good packet to show that okay, good was going, and then I'll send a bad to show that I'm not able to send this missile. So I'll send this from n0, port is my 3456. Okay, I'll send the file which is the hello file, and yeah, so if I send this should come, and yeah, so you see I was able to send and I was able to receive, and now this was the good packet. Okay, so good, so in terms of good packet, like previously shown, it was doing. Now we'll just skip the comparison. So yeah, see, out.txt hello is there. Now when we do the bad packet, so again I'll set just a server over here at n0 node, and then I'll try to send a missile. So iperf, then server, then port, I'll put 3456, same thing again, started the server. Now I'll do the tcp dump to here over here. I'll send the tcp dump, sudo tcp dump, and then yeah, and then I'm hearing. Now I'll send the, yeah, like I said, I'll send the missile. Okay, the packet which is missile, yeah, so missile, so this should be dropped. And yeah, now I'll send this one to n0 node, which is my server. Wait a second, yeah, local, need to see lab, not the tab, yeah, lab iperf, yeah, missile.txt I have to send. No. So I'll just send this, and this should not be received. Yeah, as you see, this is not sending. Even in that server we are not able to receive, and here if I open the txt file, see, nothing is there, so not able to receive. So yeah, see, yeah, so that this is all, and this shows that for missile packet, and we are not able to receive the missile packet, while the good packet in .txt we are able to. So both source and destination, and that is working.
We just saw how hands can protect you from a cyber attack. But why would you want to choose hands over any other available network intrusion detection system? The answer is pretty simple. Hands provides a huge advantage in terms of bandwidth and cost reduction. Our baseline comparison is with Snort, which, as discussed earlier, is a software based network intrusion detection system. Snort shows an average of 182 megabits. These values are averaged on multiple runs. Our hands, on the other hand, gives an average bandwidth of 520 megabits, giving almost 3x improvement in terms of bandwidth. This means you'll have less buffering. This was implemented on a NetFPGA based on Vertex 2P. If we use the latest NetFPGA Sume for the same application, we would estimate a bandwidth of approximately 2000 megabits, showing a significant increase in terms of bandwidth. Now coming to the cost expenses. If we use Snort, you would need to install it on any of the cloud servers. The estimated cost for the major players in the cloud industry, that is Google, Amazon AWS, or Microsoft Azure, would be roughly around $200 per month. NetFPGA Sume, on the other hand, would be a one-time investment and has a lifetime of over 10 years. This would cost you approximately $50, which is way cheaper. Now, this is our timeline. Our project spanned over 5 phases. We started out by designing a RISC-V multi-threaded processor. The phase 2 focused on building the network processor on top of RISC-V processor. Then we extended it to a dual-core processor. The last 2 phases focused on designing a hardware accelerator and building the rule set. And these are a bunch of papers that we referred to. And to understand more about hardware implementations of network intrusion detection system, I would suggest going through framework for the network FPGA based NIDS. Thank you.